This is my lab for a video presentation. This lab studies the motion of an object attached to a spring oscillating in the y direction. We use Tracker to capture observed motion and GlowScript to model predicted motion. Then we compare the observed and predicted data. We also graph the changes in kinetic, gravitational potential, spring potential, and total energy. This is important because it has real-life applications, such as in extreme rope sports. The two main fundamental physics principles covered are the energy principle, which states that the change in total system energy must be equal to all of the energy transfers with the surroundings, and Newton's second law, which states that the rate of change of momentum is directly proportional to the resultant force applied, as well as in the same direction as that resultant force. We use Newton's second law to update the velocity and position of the object. We set F net equal to the force of gravity plus the spring force. We also use the energy principle to calculate kinetic, gravitational potential, and spring potential energy. Finally, we use the equations to find various spring force values, such as the spring constant and the length of the relaxed spring. We assume that the spring force and gravitational force are the only forces acting on the system. We also assume that the net force changes little between time intervals and that the origin is at the point of attachment. We use this model because it contains suitable time intervals during which the net force changes very little. Additionally, the model shows the mass moving in two dimensions, the x dimension and the y dimension. To summarize the results before diving in, I found that the observed data varied a little with the predicted data. Additionally, energy changes did not line up accurately. In Tracker, I set the length scale to 0.7 meters, which is the distance from the attachment point to the center of mass. The time between frames is 10.5 seconds, and the origin is the attachment point. This is a clip of the object moving in Tracker. For the initial conditions, I set the ball's mass and the initial position and velocity vectors based on values from Tracker. Then I found the spring constant and relaxed length based on the equations mentioned previously. Additionally, I specified the vector L and the values for L hat and S. Then I computed system energies by providing equations to find kinetic, gravitational potential, spring potential, and total energy. I set the time of the while loop to less than the maximum time frame in Tracker. Then I found the vectors for gravitational and spring force and solved for F net. Then I used the momentum principle to update position and velocity. I also updated the spring by updating the L vector, L hat, and S values. Finally, I calculated the energy changes by subtracting the initial energy values from the final energy values. In the energy change graph, the spring potential energy varies inversely with the gravitational potential energy. The total sum of the energy changes is zero, as expected by the energy principle. The change in kinetic energy fluctuates throughout the graph. In the y position versus time graph, the predicted position overpredicts the observed y position at the peaks. This may be due to energy dissipation, such as drag force in the positive y direction, opposite of gravity. In the x position versus time graph, the predicted position overpredicts observed position at some points and underpredicts it at others. This may be due to energy dissipation as well. One source of error may have been that forces may not have been constant during the time interval. To fix this, we could look at a smaller time interval. Another source of error could have been inaccurately plotting point masses in Tracker. We could fix this by plotting the points more carefully at the center of the object in Tracker. Additionally, there could be energy dissipation due to forces such as drag force, friction, etc. We could fix this by expanding the model to account for these factors. For the first question, the energy principle is satisfied because the total sum of energy changes is zero, as seen in the plots of the energy changes. Energy is conserved because it is transformed into different types of energy. For the second question, I found the oscillation period from y position data to be 1.519 seconds and the oscillation period from x position data to be 1.614 seconds. These two values are different because the object is not moving in a perfectly circular motion, so the length of the oscillation period from x position data is longer. In conclusion, this lab covers important physics principles such as the energy principle and Newton's second law. The predicted results varied a little from the observed results, but were similar overall. Thank you for watching.